Hey guys, welcome to another video from Foolish Engineer. Last time we had designed a current regulator using LM317 voltage regulator IC and current regulator using combination of transistor and Zener diode. This time we are going to design another current regulator using just transistors. So let's go for a ride. The very first thing we need to ask is, what is a constant current regulator? Well, any source which provides constant current irrespective of any change in output load or input voltage is known as constant current regulator. Let's see the basics of current and voltage. When we connect a normal voltage source, let's say a battery, to a resistor, then the current flowing through a resistor will be the division between voltage applied to it and its resistance. Well, this is nothing but the basic Ohm's law, right? So, with this logic, the constant current regulator changes its own resistance in order to give the constant output current, which may result in changing output voltage to pump the current in the load. So, when the load current is supposed to be increased, the regulator decreases its resistance, and when the load current is supposed to be decreased, the regulator increases its resistance. But why do we need a constant current regulator?
Wait a minute!
Well, the current regulator are very useful for driving the strings of LEDs. And it is also useful for capacitor charging circuits, which we need accurate timing. So let's see how we can design a current regulator. You know what? A transistor can provide a regulated supply of current. We can use BJT or MOSFET depending upon the current and voltage requirement. So we can add a load to the transistor. We can bias a BJT to its base and a MOSFET to its gate. For now, we'll consider a BJT. Well, the regulators have internal feedback loops, and that's how every regulator provides constant voltage or current for any input voltage fluctuation. So to gauge that stability, we need to provide some feedback to any discrete circuit which will give the regulated supply. So we need to bias the BJT such that it gives constant current. There are multiple ways to add a feedback path to this transistor. We can bias a transistor in many ways. Last time we did with the Zener diode. If you haven't seen that video yet, you can watch the video by clicking on this card above. This time we'll design a current regulator using 2 transistors and 2 resistors only. The combination of transistors can be done like this. Here we have used BJTs, but we can use MOSFETs as well. Let's name them as Q1 and Q2. We will add 2 resistors to this circuit and consider them as R1 and R2. R1 is the current limiting resistor which provides biasing voltage to this Q1, and R2 is a very important part in this circuit. The transistor Q2 is the feedback part to this circuit, and R2 is the current sensing resistor. And the load has to be connected between input source and collector of Q1. Let's see the working of this circuit. Initially, when we supply the voltage, the current flows through R1 and it turns on the transistor Q1. When Q1 turns on, the current flows through this path and flows through R2. This R2 resistor decides how much current should flow through the load. As current through R2 increases, the voltage drop across it increases as well, because the voltage and current are directly proportional to each other. Once its voltage drop reaches up to base emitter voltage of transistor Q2, the Q2 turns on. When Q2 turns on, the current flowing through this branch will try to follow the least resistive path, which is this. And Q2 pulls all current flowing through this R1, which turns off the transistor Q1, and current starts decreasing through this load path. And eventually the voltage drop across R2 decreases and then Q2 turns off again. Well, this feedback loop ensures a constant supply of current through the load. And that's how a constant current regulator using two transistors works. We can set the load current from this formula. Let's see an example. The output current required is, let's say, 50 milliamperes. The input voltage is 8 volts. And our load is an LED which has forward voltage drop of around 2.2 volts. Let's calculate the value of R2 with this formula. The value of R2 will be around 14 ohms. Let's consider the HFE of the transistor Q1 will be around 50. So from this formula, we can calculate the base current of the transistor Q1. So base current requirement is only 1 milliampere. When Q2 turns on, the voltage drop across R1 will be approximately equal to the source voltage. Hence value of R1 can be calculated with this formula. So R1 will be equal to 8K. Q2 can be a general purpose transistor like BC847 or BC547. But Q1 should be powerful enough to handle the load current and power dissipation. So ICE of the Q1 should be greater than 50 milliamperes. Now the power dissipation of the circuit can be calculated as voltage drop across the component and current flowing through it. So power dissipation across R1 will be only 8 milliwatts. Power dissipation across R2 will be around 35 milliwatts. And power dissipation across transistor Q1 will be around 255 milliwatts. We need to select a transistor which can handle this much power. Well, that's how we can design a constant current regulator using transistors. Let's see the simulation. This is our circuit diagram. This is the Q1, Q2, R1, R2, and this is the source. All values are based on the earlier calculation. Now we will simulate this. As we can see, the output current is nearly 50 milliamperes. In the calculation, we have considered the VBE of 0.7 volts. But practically, this is not the actual VBE on of the transistor. So we'll need to change the resistance to get the current of 50 milliamperes. If we change the input voltage from 8 volts to 10 volts, still the output current remains the same. Now, if we add one more LED in series, which means if we change the load, still the current remains 50 milliamperes. Well, there are various advantages of this circuit. This circuit is very easy to implement and it gives very stable current regulation. Unlike the earlier circuit, it has very low power dissipation. Well, there are some disadvantages as well. However, this circuit doesn't provide stability in the temperature variation. And due to the limitation of discrete components which we are using, we can't use this for higher current application. Well, that's all about the current regulator using two transistors. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to my channel, and finally, thanks for watching.